When I started, people called it snake oil and like there's no hope. And now everyone works on some form of intervention. So great successes. Great, fantastic. There is a lot of interest from VCs and people that want to make money. Also great, because that kind of like creates a lot of hub and companies are being created and that accelerates progress. So all of that, good and positive signs. VCs even come like to Europe, or like European VCs are considering it. Even large pharma is now very slowly and tentatively looking at aging as an intervention field. And they're creating kind of like sometimes collaboration with aging scientists. So again, like fantastic, large pharma is on board. That's a great win. So all of these are wins. The downside is still most of the public is not on board. None of the politicians are really interested. And kind of, there is not enough governmental funding, because VC money is fine, but that usually is spent in a certain way. And what I'm afraid of is that eventually the pipeline, because the discovery pipeline will be empty, because everything that we can work on and intervene in has been translated. But because no one puts money into blue science research, like blue sky research, like we just do research. We don't know what we will come up with or understand or learn. No one wants to put money into that. And that means that eventually we will have no more new knowledge that we can use. So I'm afraid that we have a dry pipeline of preclinical or like even earlier research where the government is not interested in funding that. And definitely VC will not fund basic research.
Alexandra, what is your mental model of the future? Do you think that we will reach longevity escape velocity in our lifetime? And has that view evolved for you over time?
Okay, a complex question. Right to as a good start. I really don't have a mental vision for the future. I think it's possible, and because I like that vision in general, I want to work towards it. If we reach it or not is really not so important for me. And I don't want to spend a lot of time thinking about like, okay, what's the chance? Is it like a 50% chance within the next 20 years? It's just not what I think about it. I think it's achievable, and therefore I work towards it as fast as possible, as urgently as possible. But yeah, I don't do a lot of guesswork, so I'll leave it at that.
Yeah, we're going to talk in more detail at what you actually does right now at your lab in England. I guess that a lot of people who is going to watch or listen to this are probably familiar with who you are, but for those who are not, you are Alexandra Stolzing. You are a professor of biogerontological engineering at Loughborough University in the UK. That's right in the middle of the UK, right?
That's correct.
And you're also the former vice president of research at SENS Research Foundation.
Yes, that's also correct. So a little bit of my background. As you might have guessed, I'm not from the UK originally. I was born in Germany. I'm a biologist by training. Really a very broad biology background. And I have been living in the UK and also in the US for several years. So I'm not really particularly attached to any of these countries. I usually go where there is the best opportunity to make an impact. And yes, sorry, the biological engineering title. So because I am part of an engineering department, engineering needed to be in the title. But because I work in biogerontology, I thought that's a nice combination. But it also reflects a little bit my approach to kind of aging interventions. And that is, I want to have a very pragmatic approach and using a lot of devices if possible. I think that's a very kind of nice approach combining biology and engineering, I think will accelerate our progress.
I've looked at your published papers. I mean, you have done a lot of things during your career so far. Your name is on papers on stem cell biology, regenerative medicine, cell therapies for neurodegenerative disorders like Alzheimer's, cryopreservation, epigenetics, biomarkers of aging, tissue engineering, cellular metabolism. So you have really done a lot of things, but I think the thread that binds it all together is that it's mostly around aging biology, right?
It's all around aging. Even the cryopreservation, I do because I want to have good cell therapy products going into a cell therapy, because even cryopreservation can induce aging in cells. So if you do it incorrectly, what you would give patients would be cells that are already senescent. So this is, yes, you're absolutely correct. Everything is bound together by aging. And it also shows you how complex aging is. For me, it is kind of a mirror of like how difficult aging is. You can't stop with being an expert in one little thing. Aging is a very complex thing that is happening cellular level, protein level, goes up to the tissue and kind of organism level. So I think that's why it looks so broad. But partially this is also because what I try to do is I try often to combine knowledge from two different disciplines and think how I can translate what I learn in one discipline to another one, which makes me more of a generalist. A lot of academics don't do that. They are specialists in one thing and one thing only. I'm a more generalist, and I try to find the synergies between different fields.
How do you decide what you want to focus on?
Ooh, that's a difficult one. It was a development. So I started out when I did my PhD in trying to understand aging. And I think that is a general trend with a lot of academics, a lot of people going into aging. They first think, okay, I need to understand that thing. And then very quickly I learned, okay, I will never understand it. It's so complex. Let's look at what intervention I can have now and here. And that led me to work in the stem cell area that I did. So I progressed from neurodegeneration and brain aging to stem cells because I thought that's the cure. So I need to work in that area. I need to understand stem cells. And then I progressed further into the more engineering areas because I understood, okay, the way we are producing cells, the way we're delivering cells into a body, all of that plays a role in how successful I am with the therapy. And then one step further, it's like, okay, how I freeze the cells is impacting what comes out at the end of the therapy. So you see kind of the progression. It was mostly not a free choice. It was more, what do I need next? So what is my kind of in my vision? So mostly I focus on the brain, or I try to focus on the brain and the brain aging and the therapies that are towards keeping the brain alive, because I think that's the most important organ. We can live without a leg, we can live without a liver, we can't live without the brain. So that was always the central theme that I tried to keep. So I was always looking, okay, what do I need next? And then I go into that area. So it's not by random choice, it's more what next, what tool do I next need, and what knowledge do I need.
It's been a natural progression there.
Yeah.
If we back up a little bit, you were born in Bonn in Germany.
Yeah.
That's actually quite close to where my father lives. He lives in Oberhausen. Maybe you know of it.
Yes,
and it's the birthplace of Ludwig van Beethoven.
Mm-hmm.
Also,
I did stand in front of the house. That's the closest that I ever came to kind of visiting that place.
What is it you think that made you so interested in this field and wanted to dedicate your life and career to it?
Because it's enjoyable to be alive. It's a very simple fact for me. It's enjoyable to be alive. And I think life is beautiful. It sometimes can be cruel. It can sometimes be not nice, but you can then remember back the times that it was nice. So that for me made it kind of like once someone opened my eyes to me and like, look, this is nice. Why don't we keep this? And I was like, yeah, well, actually, that's a very good idea. Actually, why not? And at the beginning, I thought a lot about what area to work in that has the biggest impact. So I thought a little bit, okay, is maybe chemistry the way to go? Is it another area? But I very quickly learned that biology is the thing that comes kind of like quite natural to me, and that's the area that I can maybe hopefully make some impact in. And yeah, that's how I came to be in this area. And it was a time when aging or aging intervention wasn't really a thing. It was even hard finding a lab that had aging in their portfolio. So I was back in Germany, and when I selected or was looking for a PhD lab, and I had 3 choices in Germany. Interestingly, all 3 were in Berlin. One working on fungi, so not really a great lab to work in, I thought, and 2 working with human cells and on human aging. So that was the choice I had in Germany. Not a lot. And I think I was very lucky by ending up in the lab that was most open to aging interventions, which again was not a thing when I started. A lot of people told me that's all snake oil and it's fantasy and it's crazy. Only strange people work in that area.
When was it you first discovered that you wanted to try to cure aging?
I think I was pretty old, so I think I was 17 or 18. So I was a latecomer. Like maybe I was too naive. I was not exposed a lot to death in my family, so I was just not thinking about it. But when someone mentioned it to me, it was like, yes, instantly it clicked, and it was like, yes.
But also, it's still not very well known that you can do something about it.
Oh, that's correct. When I talk to friends, colleagues, acquaintances, I mention it, like I mention what I work on. And even the very highly educated ones, the ones that are like reading all the news, all the books, everything, where you think like, okay, they know everything. They look at me and like, wow, so that's real? You can do something? And so it's surprising with all the podcasts out there now, all the websites, they're still not reaching most of the people.
Yeah. I'm thinking of one thing you said, that you didn't have a lot of choices back in Germany. At what time period was this? Because I immediately thought of Cynthia Kenyon and what she said when before she made her discoveries in C. elegans, that they called her lab, I think, a black hole for biology or something like that. And she said they told her that don't do aging biology because it's a career suicide. And that was, I think, in the beginning of the 90s.
Yeah, for me it was round about 2000.
Okay.
That's when I looked around. So,
but we've come at least maybe not. We've not penetrated to all of humanity yet with this information, but I think we've come a long way still, at least when it comes to research.
Yes, absolutely. Like, look at Germany. We have at least the Max Planck Institute now and a Leibniz Institute, both for aging. So, yes, we have come a long way, but it's still not enough. It's still just a tiny drop in the ocean.
Did you ever feel personally discouraged from this track?
No, never. It never was for me. All the barriers, okay, you have to live with them, you have to find a way around it, but it never discouraged me. I never thought about like giving up, because what does it mean to give up? It means nothing will happen. We will die. So it's not a nice alternative. So
But what did your professors say?
They were very positive. They kind of encouraged me. They helped me. Luckily, they're still in contact. We're still working together on like this aging track. He never went full heads on into the intervention side. He wasn't against it. He was just not. It wasn't his career choice, and I think he is not as dedicated maybe like me. He doesn't feel it as urgently to do something about it. So he encouraged me. He still works with me. We have nice discussion around proteins and protein aggregates and lysosomal aggregates and how we can get rid of it. So it's nice, encouraging, but he couldn't kind of guide me or mentor me. Like he wasn't the person that was networked in the longevity field. Again, the longevity field didn't really exist. So
right. And now there's something called geroscience. Would you say that you're a geroscientist?
It's all names. I think it's a good name, geroscience. I usually call it biogerontology science, biogerontological science, simply because geroscience could also mean having phones with big buttons. Like the more kind of like helping the elderly, not doing something against the aging process. So that's why I try to kind of put the bio in front of it. But in the end, it's all names. It just doesn't really matter that much.
Before we move on to what your focus areas exist of today, let's just talk a little bit about SENS Research Foundation. I mean, it was started by Aubrey de Grey and organized around tackling 7 different types of damages that accumulates as we age. And one of the ideas was that we should not intervene in the normal metabolic processes, but just let them run their course and then repair the damage. Is that a valid description of what SENS, what the original idea with SENS was? And is it still a valid approach to actually solve aging this way?
Okay, let me paraphrase it. I think you got like 90% of it. So yes, so the metabolism is super complex and it's tightly regulated. So anything you're changing, the system will try to kind of counteract. That's why it is very complex to interact in this complex, very highly networked system where like you kind of like do something in one area and everything is changed and can also negatively be changed. So that's why it's very complicated. So I think his idea, and I don't know what went on in Aubrey's head, so I'm trying to like just see it like from the outside. But for me, it made sense to say, okay, what we're intervening in is not the metabolism because that's too complex, but we wait until there is damage. And we intervene before there is pathology. So there is metabolism, then there's damage, and then there's pathology. So once we have pathology, that's too late because then something is already broken. So it's better to kind of like fix the damage while there is still kind of like a living tissue around it that's still functional. And what he really tried to do is to break down a very complex system into like smaller and smaller boxes so that it is easier to talk about it. And there have been certain attempts to like, how many are there? I think 7 is a good number. It's easy to kind of like overlook. And you can fight over like, is there maybe an 8 damage type or is it only 6 damages? And again, for me, that's not so important. It makes sense, the categories, and I think they are still valid. So because that was the other question. So he came up, I think, with this idea around about 2008. And yes, it's still a valid thing to try to intervene in the aging process. I think it makes sense. Yes, you could also try to intervene in the metabolism. The more we understand it, the easier it is to intervene. But it will be more complicated and maybe there are more failures. But I wouldn't say don't do it. I just say good luck. It's maybe easier to work on the damage level.
Yeah. Okay. So that's an important distinction. I think that maybe it depends on how old you are today and what diseases you have. But I think that a lot of people maybe in certain age categories are still holding out hope for that there will be good interventions. But you say that the more pathology it is, the harder, of course, the problem will be to fix.
Yes.
Can you mention a few of those damages that happens as we age, and which ones do you focus on in your research right now?
So let me maybe list the ones that I worked on. So there is lysosens. So basically that's the area where you look at intracellular aggregates, and that's aggregates of proteins, lipids, DNA, basically all the garbage that the cell can't get rid of. So yes, the cell has systems to recycle this material. But there are levels when the damage is so high that the capacity to remove it is not enough. And so over time that builds up. And that more and more blocks other functions of the cell. And so in a lot of neurodegenerative diseases, that is what a lot of times is happening. So you have a lot of intercellular proteins accumulating that are then leading to inflammation of cells, to cell death, to kind of misregulated cells. So when I was working on intercellular proteins in the past, I tried to find ways of upregulating our removal of this intracellular aggregates. And then definitely
how can you do that? What is a way to upregulate that?
So for example, the cell has so it's getting more complicated now. So the cell has one big protein called proteasome, and that is mainly responsible for degrading all the damaged proteins. So there are a small molecule that can upregulate that capacity of this molecule to get rid of garbage. It's an area that is not well investigated, not well researched, but that's one thing. And then I worked more on the cell side. I worked on the microglia cells. They are the macrophages that are sitting in the brain, and they are responsible for basically finding this material, eating it up, so engulfing it, and then trying to digest it. And for recognizing this material, they have receptors. So I looked at ways of upregulating the amount of receptors so that they can actually eat more of the material. And then very soon I learned, okay, that's kind of, yes, it's working, but then they also become broken because then they're overfilled. And that led me to the idea of doing cell replacement. So because then I learned, okay, they senesce, and so you want to then replace them. And that came kind of for me as in the idea, okay, that's nice. So we can just give the brain new microglia cells then. And then they can do more kind of cleanup. And we could do that on a regular basis, just kind of supplying the body with new cells from the outside.
I think some people might think, well, can we really replace brain cells?
Okay, now we go into nitty-gritty of brain cells. So I worked on cells that are the support cells of neurons. Right. So I didn't work on neurons. So, and if you have the theory that our memory, personality is mostly encoded in the neurons, and then we can debate long for how it is encoded. And I'm really not an expert on this. But so I would say it is neurocentric, where the memory is stored. So I was only working on the support cells, and I would think, yes, there is no information out there that says that personality is stored in microglia cells.
Right,
so
right.
And that's why you can easily replace them.
Yeah, and I think that microglia is you have to tell me if I'm wrong here, but it's kind of a new research area. I mean, compared to neurons, or
no,
but it's not as well known.
It's maybe not as well known, but the microglia cell has been discovered many hundreds of years ago. So it's like that cell is known, is well known. But yes, it has not been in the center of attention simply because most people are looking at, yes, neuronal loss is responsible for kind of memory loss in Alzheimer's. So, and
has its role also been known for so long? What the microglia does?
Maybe not. So I think it was always known it's a support cell. It was long known that it's involved in the inflammation immune side of the brain. And I think further roles have only been discovered, yes, in the latest years. So, but it's not like we have a surprising new cell type here.
Right. Yeah. Okay. And so you started with lysosomes here, and we traveled to the brain. And we were talking about damages and your focus areas now.
So repleniscence is another area, and that is the loss of stem cells. So here it's not like a damage that accumulates. The damage is here basically a loss of stem cells. So the body having less hematopoietic stem cells to make blood, or having less mesenchymal stem cells to make new bone, or having less neuronal stem cells to make new neurons. But that side is a bit debatable in humans. And then we have other areas like mitochondrial damage. I think at least mitochondria are now in everyone's mouth, probably better known. So they're kind of the energy provider of a cell. And because that's a very tough job, they become very old very quickly. And so people have been thinking of like removing them, replacing them, modifying their functions. So that's another of the SENS strands.
Yeah, mitochondria is interesting because some people think that might be. I mean, there's some schools of thought that think that maybe like mitochondrial dysfunction and inflammation are the main culprits, and everything is downstream of that. And I think that mitochondria is one of those that sometimes gets mentioned as maybe that's the real bad guy. Or the mitochondria is not, of course, the bad guy, but when it's not working well.
Which would lead us down the avenue of how many aging theories are out there and how useful are they, and are they not just a tool for academics to make a name?
Right, could be so.
So are they the main culprit? Is it really important for us to know if they are like the second in the list or the third? We need to replace them all. They need all to be functional. So in the end, we have to address all of these issues. And so it's kind of like, again, a loss of my time or discussion time if we say, okay, our argument is all about like who is now higher in the hierarchy of like importance. And I would say like instead, let's address them all and hurry, because we're losing time by discussing what's more important and what's slightly less important.
I think though that maybe sometimes the argument is that if we don't know what we're going to focus on, maybe we're betting on the wrong horse. But you're saying we have to bet on all the horses to address this.
We have to bet on all the horses. We have to cover our ground. Yes. And then we can go into the debates if it's 7 SENS strands, or is it this 12 hallmarks, or is it the 9 hallmarks? And I think there is a certain number of things we can address. If it's 9, 7, 12, it doesn't really matter. I think they are like, as long as we cover most of them, we hopefully will see some improvement. And then we can find out later which one was giving kind of like more lifespan extension than the other once we have actually done it.
Yeah.
So we're referring to a paper here, right? The Hallmarks of Aging, and suggested there are 9 categories and then later 12 perhaps. And it's like an advancement of Aubrey's 7, I guess. What do you find to be the virtue in the hallmark that does it add something to the original like SENS categorization?
So from the scientific side, I think it is not adding a lot. It has refined it. It has kind of like changed it a little bit. But what was impressive was that one picture is in every single publication or every single lecture to the public. So somehow that figure captured the imagination of the people. So for me, it was an impressive paper because it was suddenly people paid attention. Suddenly they used this as a form of talking about like intervention and how likely it is to have an intervention. So I think surprisingly, yes, this had a huge impact. So, and I'm very happy that they had such a success with it. And we need more such papers. It would be awesome if we would understand why it was so attention grabbing. What was it in this paper? Was it just the figure, the text? What was it that suddenly it was in everyone's mouth? Everyone used it. It was so useful. Fantastic. We need more of these papers.
Yeah, so we shouldn't really, get to the bottom of the actual categories, but just how they were presented.
I think the scientists should get into their in-depth discussion. Exactly. Okay, are these 9.5, or 10? So that's kind of a very academic discussion, and the experts should have it. But in terms of like talking to the public, we should understand like how we can better present it so that people suddenly find it interesting or easy to talk about. I think it's a little bit like the blue zone concept. Everyone talks about it because somehow it is easy to grasp. Maybe it's interesting. And if I ask colleagues of mine, they have heard at least now about the blue zones. So now this leads me then into like talking about aging and aging intervention. But yeah, more and more people have heard about the hallmarks. And somehow, like the telomere. So the telomere shortening as kind of the first clock, however bad or good that was. Again, it was easy for people maybe to understand it or have a concept in their head, like something getting shorter and shorter with time was something they could grasp. And so everyone that I talk to about aging interventions usually, so telomere or something. So it's something that is easily grasped, and we should definitely do more of that.
I mean, that was also kind of detrimental. We were talking about mitochondria just a few moments ago, but for a long time it seemed like people thought that if we just add telomerase, we will solve aging, and it's not that simple.
That's correct. That's then on the overselling, what we can do or can't do. But I think we will not get rid of that. The whole finance system, the whole communication system is so skewed towards always overselling. I really don't know how we can get out of this. Every grant I write, there is a section where basically they ask me, okay, and in 5 years you will have cured all of aging in the world, and I say yes, definitely. If you give me this money, I will have.
What do you mean? What do you mean by that? Is that actually?
Yeah, it is. So what a lot of governments want to do these days is they want to show that there is real world impact in after they have given me research money, that there is real world impact. So now I have to always show with my research how definitely now I will cure Alzheimer, or I will cure cancer, or whatever you work on. And that means that we're constantly bombarding the public with these promises, because then someone reads it, they read the public abstract where I promise to cure Alzheimer, and then they get fed up with it. And I think that is bad. So we have to be very careful how we balance this, promising something, that we work on something, but don't overpromise. But then kind of the funder, they push us into it, because otherwise we don't get money. So it's like it's a vicious cycle, actually. So yes, with this telomerase, you just add telomerase and then aging is cured. Yes, it's a simplification, and it's wrong. And we should be careful how we address it and that we address it.
Maybe we won't stay too long on telomerase, but I think it has also been the case that maybe people thought that, okay, telomerase is dangerous. We can make cancer cells proliferate, but there's also a lot of interesting research still going on telomerase that is really promising. So you shouldn't count it out either.
Yeah, absolutely. It can be bad, it can be good. So as you said, there are some cancer cells where like blocking the telomerase, it might be beneficial, but there are other cell types that still need it. So that's the complication of like aging. It's such an intricate network, and everything seems to be linked, and everything is different in every cell type. So
you're playing whack-a-mole for a living.
Yeah, a bit.
Okay, so where were we? You mentioned replenisense, and then we
got off topic.
Yeah. You want to continue on that line, or do you want to go more on like what you do now? How would you want to continue?
Yeah, we can continue of like what I'm doing currently. So currently I try to address senescence, which are senescent cells and accumulation of senescent cells. And what I'm trying to do is to get rid of them. So one way of doing it is to look at what's on the surface of senescent cells. And then I can either use devices, or I can use cells, I can use molecules to attack them. So people might have heard about Senolytics. So basically drugs that specifically kill these senescent cells. The downside of these drugs is often that they are not very specific, because they target every cell, and some cells are damaged by these drugs. So one way of like modifying that slightly is by having something on the surface of a cell that's specific to senescent cells, and the drug targets only that one, so that the drug can't even get into healthy cells, which makes the drug a little bit safer and hopefully more efficient, because then we can go higher with the drug dosing and then kill off more senescent cells. So that's the very simplified method. And
so it's looking for like a common denominator for senescence.
Yeah, well, if they are a common denominator, it would be nice. I think that's to be discovered. So there's research area of like, okay, senescent cell marker is a very prolific one, and we don't have good markers. And so
there's a lot of heterogeneity in senescent cells in different tissues, right?
It looks like they are very different from each other. How much they're different is still up there, and how many different subtypes are there, and then how much different are they? Because like heterogeneity is like, what granularity level are we looking like? Do they have 10% of their genes differently expressed? What does it do to my surface marker? We don't know yet. It's too early. So unfortunately, it's an area that we still have to like do more discovery research to know how homogenic or heterogenic the cells are.
Was your paper that was published, I think, last year related to this?
It was related to it. So there we used a surface marker that was already known, and more or less we used it to have a more refined senescence culture so that we can better test Senolytics. And we also wanted to explore a little bit how much senescence is spreading. So a little bit like a virus, senescent cells is spitting out substances that make surrounding cells become senescent as well. So we wanted to better understand how much that is going on, what factors are involved, and are the secondary senescent cells the same as the primary? Because that was alluding to this heterogeneity. Like, so the first senescent cell type might be because I don't know, UV light has aged it and it has become senescent. But then that senescent cell is producing now substances that make another cell senescent. But it's another damage type. So is this secondary senescent cell now different or not? So that's kind of what yes, it is slightly different. How important that difference is debatable yet. We were mostly interested, can we still use the same drugs to kill the cell? Mostly they seem to be dying in the same way. There's a slight difference, but it's not significant enough, I think, to be of great importance.
Just as with the telomeres and telomerase, it's a double-edged sword with senescent cells, because they seem to do a lot of important stuff as well. Is this more when we are younger, when there is no pathology, that they actually do serve important roles for us, or is it also when we have accumulated senescent cells, but some of them are still doing what we want them to do, so to speak?
There's both. So we have some of these cells playing important roles when you're young. Wound healing, pregnancy is usually just when you're young. Wound healing could happen like over a lifetime.
Right.
But what I think is different is that senescence plays a role in blocking your cancer cells becoming too cancerogenic. So they the body tries to shut down your cancer cells. And most cancer rates increase with aging. So definitely they become even more important to be functionally kind of active to block your cancer spreading.
Yeah.
So I wouldn't say they are more or less important if you're young or old. They're always important. And yes, we have to always pay attention how much we are killing or where we are killing them. So yes, it's not super easy to just go and get rid of them. I mean, like looking at the mouse data, it looks easy. Is that transferable to humans? First indications from clinical trials look positive. So maybe it is that easy. But I think, as usual, we will say, yes, we need more data. We need more clinical trials to better understand it.
Right. Just hang on a bit. I have to see what's happening with my dog. That's a recurring theme when we record these podcasts.
So we will edit everything too. So
it's fine. Just bring the dog in, and it becomes a thing. Show him on the camera.
It's our gimmick, exactly.
Everyone loves videos of dogs and cats. Why not make it a feature?
Oh, you cannot compete with that. Maybe we should dance too a little.
Yes. How is it?
Are you done now?
Yeah.
You finished the podcast?
Yeah, we have solved it all. I told Patrick the secret ingredients, and now he will live a very long and happy life.
Oh, that's perfect.
But we also said we need to bring the dog into the podcast, and also we need to dance.
I think, I mean, she's talking to me, so maybe that's what she wants, to be on the podcast.
Yeah.
Okay.
We were at SENS and SENS damage strands, and now we were like what I am doing in Loughborough.
Yeah. And about senescence, I mean, there's been a lot of talk about Senolytics for 10 years now or something like that. Yeah. Maybe 8 years.
8 years.
Or something. Yeah. But you're still looking for the good markers to actually target these cells in the best way possible. So where are we? I mean, people are always wondering, okay, so when can we get the first senolytic drug on the market?
Yeah. And for everything you need biomarkers. And so part of the surface marker discovery is not only to make senolytics better, but it is also to have a good biomarker to actually detect senescent cells in vivo. And that's still a big problem, because in the moment, what we have to do is cut mice or human tissue in little pieces and do a staining that's not very good in telling us if there is a senescent cells or if there's no senescent cells. So unless we're developing biomarkers that I can measure in a living organism, it's super tough to develop senolytics if I can't quantify if my target was actually now going down or not. So the current markers that we have are simply not very good, not very useful. So that's part of why I wanted to have a senescent surface markers. Most current markers are measuring something inside of a cell. And that's always harder to develop into a biomarker than something that's on a surface, because then I can have like a PET scan. I can kind of create like a peptide that comes with the fluorescence signal, or I can put like an isotope on it, and then I can use it to actually detect it in living people. And that would help a lot, like streamlining clinical trials and making them more precise and quicker. Because in the moment, what people are relying on are secondary, basically kind of like one level removed markers. They look at like pain in your knee, or the speed of walking, or maybe on a memory test. All of these tests are very unprecise. They're not very accurate. So I think it would be great to have this as a biomarker. And
that's also interesting, because you said that how your career has been a little bit defined by how one thing led to another.
Yes.
You realize all the time, okay, I have this, but I don't have that, right? And
yes.
so that's how you go to the biomarkers of aging, and that's also a very, very important field in biogerontology now, right?
Yes, it is.
Because we have to know what interventions work. Patrick is about to say something now.
Well, I just wondered, do you have students to direct to these kind of problems? I mean, you can't do everything yourself.
Oh, no. I mean, like, as most scientists higher up, the only thing that you do is manage. You find the interesting problem, and then you dip a little bit into it and see, like, yeah, that looks good. And then you give it to a very clever scientist and say, like, now you figure it all out. And then, yes, we help in that process and we give directions, but no, I can't do it all alone. Like, it's always a team. It's always, you are as successful as your team members. None of us works alone, and we also work a lot with collaboration. So I have, as part of this biomarker study, I have here in the university, we have like 4 other teams being involved in it, and they all have like 20 years of experience or more. So it's always a team effort.
Patrick?
So maybe more on the biomarker side. So why are they so great, and why do we need to kind of like invest more in them? With all of the things that we're working on, lifespan, it's taking a long time. Even in mice, it's 2 years until we know, yes, this works or this didn't work. So that's already kind of like way too long. And that's one reason why we want these biomarker of aging or age rate biomarkers. They're slightly different of what they're measuring. So we want them to be able to predict if something works or not, like on a shorter time frame. And then we also want them in humans, because again, we can't run a clinical trial over 50 years to see if someone lives longer or not. We need something that we can measure to see, yes, this works now or this doesn't work. And so what we're currently working on is a breath-based marker of aging. So the compounds that we're breathing out, they are coming from our metabolic cells that are active, and they're very small compounds, and we breathe them out constantly. And I think this came to me during COVID, as a lot of, I think, interesting ideas came out of the COVID pandemic, because everyone was scared going to the doctor. There were no nurses around to take blood. It was insane going into a hospital just for like a prick of blood. Like, you wouldn't risk it being exposed to all of the people around it, and you wanted to kind of minimize the burden on the hospital. So I thought, okay, what else is there that we could measure? Is there something that we could maybe measure at home? And so I started looking at these biomarkers and thought, okay, that has not been developed for aging yet. The breath-based marker came, I think, initially from the cancer study, like all these cute little stories where they say, okay, a dog smelled that someone had cancer and another patient not. And the same is actually true for old people. Dogs can smell people that are about to die. Some dogs can smell Parkinson, and that's real compounds that they're smelling. So it's not like it's made up. And with a mass spec, you can capture all of these. And what we're hoping to do is come up with an alternative to kind of like an aging clock. So something that you can measure in the breath of a human being, and that you can hopefully in the future then do at home. But so in the moment, we don't know it will work. It looks good, but we don't know. And then the second step would develop that into like a product that people at home have, like a little device, like your ketone bodies or your COVID test or your alcohol test. It's all the same device, and we would hopefully have something like this that people could use, and then you could do your own intervention, maybe going on to diet, fasting, or exercise, and you can see if my markers go the right or wrong direction. And so I think that's just a tool that we could give the population, like the people that want to do something now and want to see it. But it would also help with clinical trials in the elderly, because a lot of the problems is getting the elderly to participate and bring them to the hospital. Right. So having something where you don't need a nurse or a doctor to take a sample will make, again, clinical trials hopefully cheaper by having just a normal person doing that testing and then sending the data to the central clinical hub that then looks at the data.
How far along are you with this work?
We just started a month ago to kind of like collect our human samples. So we are 1 month in. We have 11 months to go. So we're looking at collecting breath from 300 people. And we're looking at frail elderly people, but also we will do like everyone from like 18 years to like 65. So we will have like a baseline, and then we will have some elderly people that we're observing. And the study is designed so that we look at like who will have a fall. So we're expecting a third of our population to have some form of a fall. And then we let them come in again and like do another test to see, once, can we predict who has a fall? And can we see who is recovering quicker? So hopefully we will also have prediction tools then. Not only that we can say, okay, this person is biologically older. That's why that person is more likely to have a fall, but also who has what we call resilience, so repair capacity left. And that hopefully will give us information of like intervention pathways. So what we want to get out of it is understanding, okay, so this pathway seems to be always upregulated if someone has a lot of resilience, so repair capacity left. And then we can maybe find an intervention that upregulates it even more.
What made you decide on choosing falls as a way to measure this?
We needed some form of a stressor. We needed some form of stress. And because we don't have a medical school, I couldn't do the thing that other people were doing and say like, oh, I take a certain disease population, or I take everyone that has like a surgery. That would have been a very nice intervention, because surgeries are brilliant in that regard, because you know when they are doing it, you know when the patients are coming in, you know how long and intensive the surgery is. So that would have been perfect. But Loughborough's has no medical school, so it was just not possible. We needed then something that is happening in a normal elderly population, and falls are the most frequent stressor that's occurring in the elderly.
It's so interesting, that work. When I read about it, I found it completely fascinating.
Okay, great. I hope fascinating.
You said there's 11 months to go, and what will you know at that point? What do you hope?
Hopefully at the end we will have really like a number of volatiles, they're called, these small, very small metabolites. We hopefully will have like a number between 1 and 10 that will give us a predictor of like who's older, like who's biological older or not. And hopefully we will have an AI that does all the work, because that's the other thing why a lot of work is usually very slow is because you have an expert person sitting there and they doing the judgment of like what's in the metabolites, what's in the breath. And so we're trying to automate that process so that in the future it will only take 5 seconds to analyze instead of one person sits there for 1 day.
Right. It seems like there's a lot of possibilities now with artificial intelligence. Is that something you have used for a long time now in different types of work that you've done?
Okay, so we're not really using AI. So to be very precise, what we do is machine learning. So
Yeah.
it's not AI.
I'm thinking of machine learning is like a part of AI. So AI is the big umbrella term, and machine learning is a part of it.
But yes, to say, since I went to the US to work for BioAge Labs, that's where I first was exposed to basically machine learning and AI. And it was brilliant learning all of that. And since then, it has never left me. I think, yes, these days you can't live without it. So for everyone new that wants to learn and wants to enter the field, definitely they should have kind of like a course in that area, because it's a thing, it will not go away, and we should all better learn a lot about it and like how to sensibly use it, because there's wrong way of using it. With every tool, you need to know what's the right way of using it, what's the wrong way. You need to like have a little bit of understanding how it's being used, how it's done to apply it. But yeah, if it works, it's really impressive what it can do.
I wrote about a company called Evolutionary Scale the other day. Have you heard of them? No. They do. They've trained a large language model on proteins and through evolution, and so they can. You can prompt the model by both sequence, structure, and function, and then it will try to generate new proteins based on evolutionary data. So it has that grounding, so to speak, in evolution. And so it's really interesting, just the possibilities that are opening up to scientists now. I mean, we have AlphaFold as well. Are these types of AI something that you've been thinking about, the new modern types of AI, how we can utilize them in aging biology?
Absolutely. I mean, like the one like evolutionary AI. Yes, because there have been other organisms around that have a longer lifespan. So you could train an AI on like, okay, these are successful, long surviving organisms. These are lower organisms. What's different maybe in the way they're folding a certain cell membrane protein? So yes, absolutely. You could use it, but also in targeting. So let's go back to the Senolytics. If you know the target of your Senolytics, let's say it's BCL, which is a common target, and you can say, okay, these 100 compounds, these 100 Senolytics have been used in the past, and they all have had some activity, and you feed it into an ML, and then you, based on that knowledge, the machine will give you certain new compounds that maybe have additional features. You can tell the machine, I want a stable solution. I want something that goes and crosses the blood-brain barrier. I want something that hangs around for a long time or doesn't hang around for a long time. So yes, you can kind of choose these parameters and then say, okay, here are 100 new compounds. And then you go to your synthesizing chemist friends, you get these 100 compounds and you test it, and that can all be done within like 1 week. And in the past, you had one person, one expert sitting there and thinking, okay, I add this modification to the molecule, and maybe that makes it a little bit more soluble or lipophilic, and that took a lot of time. And now people with no knowledge of chemistry can do it by just feeding new knowledge to the machine learning algorithm, and then getting these compounds out.
It's fantastic. Is it something that you've been trying, playing with and trying to do?
Yeah,
Something?
I always, we're going back to the collaborations, I always need people to help me with that one because I'm not a machine learning person myself. And so usually I come with a problem and say like, look, I want this and this. And then I find someone that is really good at this and has the perfect algorithm because there are different things that you can do. And yeah, so I use it as much as possible. And I'm also happy that more and more of this is freely available so that I can use it myself. There's unfortunately still a lot behind like a pay barrier, but because there's new kind of like developments every day, I think a lot will be free in the future. But yes, I use it a lot.
And okay,
a little detour.
I don't know what the segue into cryopreservation is because it was such a nice segue from senescent cell to the biomarkers of aging. But maybe you can help us, Alexandra, with that.
Oh yeah, because we're using AI to actually come up with new cryoprotectants. So there you are.
I knew you could do it.
Easy. So we talked about like how you have to have like a good cell cryopreservation to have like good outcome, good therapy effects. And so in that space, we did not have a lot of development in the recent years. So I consider the cryopreservation field as similar to the aging field like 10, 15 years ago.
Yeah.
Everyone tells you not to work in that area. It's not sexy. It's not interesting. It's not having a lot of experts. And unfortunately, you have to have a lot of knowledge from different areas. You need mathematics, physics, chemistry, material science, biology. It's horrible. It's really a very complicated kind of subject area. And that's why you have so few people really working in it. And so for many, many years, we worked over and over with the same few chemicals. So we really need AI to give us some new compounds. And that's something that I'm seeing now coming into the area more and more. But it's still like there may be 3 or 4 publications that have used some form of like ML to come up with new cryoprotectants. Why do we need new cryoprotectants? Because a lot of these are still toxic. So we use them because we don't have anything better. But they are being given to patients with the cells, or the cells themselves are treated with these compounds if you have washing. But the cells are being changed by being exposed to these compounds. So it's really not perfect, but it's the best that we have. And so we just need loads of more compounds that we can like test and see what's better for the cells, what is preserving the cell in a status that is therapeutically very active and doesn't damage the patient either. So here you have to kind of like balance these two. You have to protect the cells, but you also have to protect the recipient of the cell therapy.
We jumped right into it, but maybe if someone never have heard of cryopreservation, what is a cryoprotectant and what is cryopreservation?
Yes.
Okay, in a nutshell.
In a nutshell, yes. So cryopreservation is the cooling down of a cell, an organism, or a protein to a cryogenic temperature, to minus 170 something. So really, really cold. And we do it to stop chemistry from happening. So basically, everything that is metabolism is chemicals interacting, and the lower the temperature, the less interaction there is. So basically what you do is you stop time. And there is the link to aging. Yes, you are stopping time when you basically freeze down a compound, if you freeze down a cell. And that's maybe also another link to the aging field. A lot of people have thought about cryopreservation of, okay, so this is how I can preserve my young stem cells by donating them when I'm young. And then I do a time stop. And then once I'm old, I go back to my little stock of stem cells and I use them to treat myself. So that's how today there is already kind of an interaction between the aging field and the cryopreservation field.
I'm wondering just because as it is already possible to actually cryopreserve cells, and they are used in different kinds of applications today, how are the cryoprotectants that we use in those cases affecting outcomes?
Sometimes very critically. So we had cases reported where people died because of wrong cryopreservation. So the compounds are really toxic. So if you're not really paying attention what you're preserving, your precious stem cells, for example, for like a bone marrow transplant, let's say like a cancer patient. So if you're not handling this correctly, you might kill 50% of your stem cells. And then the clinician that are using it are assuming they have, let's say, like 1 million cells. They give it to a cancer patient, and they need that 1 million cell to restore their blood-forming bone marrow. And if they don't have it, they will die because they don't have any bone marrow left and don't have cells that are producing blood. So it can be very critical. Most of the cases is headaches, other problems like mild problems. But you can have cases where people die because of the compounds and how they're being used. So that's why we say we want to replace. So one of these cryoprotectants, it's called DMSO for short form for it. That is very toxic. So it's damaging the cell, but it's also damaging the patient. So if that is left at like room temperature and you have your cells sitting there and someone forgets about the cells for like 10, 15 minutes, then your cells are dying. And so that can, in a chaotic like transplantation setting, this can happen quite easily. Because everything is happening, maybe there's delay with anesthesia, and then 15 minutes later the cells are still staying around there, and they're staying around in a toxic compound. So what we would wish for is something that is better preserving the cells without being toxic to them. So what is a cryoprotectant? You asked that question. Initially it was something that basically acted like a water molecule, but which was freezing at a lower temperature. So basically you're inhibiting that ice crystals are being formed.
And why is that important?
Because ice crystals, they rupture your cell membrane. So basically they poke holes in your cell, and then the cell just dies because all the innards are dropping out. So that's kind of how you can easily imagine it. So if at home, you know it from like the water freezing in your car in the winter, you're acting basically anti-freeze protection to the liquid so that it still is a liquid at a lower temperature.
Right. And so there are not a lot of cryoprotectants out there that we know of yet, and those we do know, they have problems. So what has your research shown so far?
So there's two things that I'm trying currently to do, and one is just replacing the toxic compounds with some alternatives. And what I do is I try to sneakily take my aging understanding of a cell and apply it to cryopreservation, because in the end it's all stress. So aging is a stress to a cell, but cryopreservation is also a stress. So by having that understanding, I try to apply my biology knowledge. So instead of like applying chemistry knowledge, I'm applying biology knowledge, and I'm trying to block the damage from being signaled into the cell and being recognized, because a lot of this damage is only short term, so the cell can recover from it. But if the signal goes through, the cell thinks, oh my God, everything ends and I need to die. I need to go into apoptosis. And so a cell just dies. But if I block that signal for a short while, then the cell doesn't know it. And if you warm up the cell again, like the cell has enough energy to recover. And there are already kind of like hints that works pretty well. And we just need more of this. So that's kind of like my sneaky way of bringing my aging knowledge into a new field, cryopreservation, and basically applying knowledge about stress in cryopreservation. And then the other bits I'm trying to do, and I come back to Patrick because it looks like he has questions.
He wants to raise his hand.
The other thing that I'm trying to do is to not only do it for cells, but to do it for tissue. And that's the big hurdle in the moment. So yes, we can handle cells. It's not fantastic, but it's working okay. But if you talk now a full organ, then no, that doesn't work so well. And now with tissue engineering or xenotransplantation, organ donations, all of that needs good cryopreservation, and that needs cryopreservation of big chunks of tissue. And we can't do that very well. We need to be better at that. So that's the other thing that I basically try to get from a cell to a tissue level. Patrick.
And sorry, yeah, you go, Patrick.
Well, I was thinking, I mean, I think there are examples of animals that goes into something like a cryohibernation or something like that. Not the full cryo or biostasis, but is there something to be learned from these examples?
So just to kind of rephrase it, so you have actually both. So you have basically frogs, for example, always the favorite example. They're getting solid, like they're frozen solid block of ice. I think like 70% of them become like ice. And yes, you also have hibernation where the metabolic activity of an animal is lower down and they're kind of like of a low energy level. So both of these exist. And I think, yes, we can learn from both. So on the frog side, we know that's mostly sugar that is doing the trick. So basically the frog, when temperature drops in autumn, they basically sense that change, the shift in temperature. And what they do is they change what they produce in the cell, and more sugar is being accumulating in the cell and is acting as cryoprotectant. And so we learn that, but
wow.
Basically we already knew that sugar can become cryoprotectant. And then on the hibernation side, I think that is less well studied because there are only a few people in the world studying it. But yes, it's also a clever idea to downregulate the activity of a cell before you freeze, because the less, for example, a mitochondria is active, the less damage is being produced. So if you basically bring the cell to sleep, there is less damage, less things can be broken. But we're not really understanding this very well. So we know a little bit of like what compounds, again, accumulate in cells. We know what systems are being kind of downregulated. But there's not a lot of translation yet happening between these two fields.
I was wondering, like, if it's so difficult to go forward or with a full cryopreservation, could one go a little bit of the way with like hibernation for humans in some way?
So the question is, can we do like a full body cryopreservation, or at least like a small animal maybe? And that question does become interesting not only for humans but also for kind of like animal banks, sperm banks, oocyte banks, kind of tissue banks. So for all of these people, this is important. And can we go part of that way? Potentially, yes, because in the end, again, we go to like, if you're reducing the temperature, you're reducing how much activity you have, how much activity reduces how much damage you have. So yes, you're extending the time span until like damage is too much and you have a broken system. So potentially, it's possible. Is there anything out there yet? I'm not aware of it. So I mean, like the most progress we had in that area is the kidney of a mouse being vitrified. So an alternative to cryopreservation, but basically the same thing. You're reducing the temperature. Has been like a whole kidney has been frozen and then transplanted into a mouse, and it was still functional. That's still a very small piece of organ. A human kidney is several size larger. So we have still a way to go.
That was quite recently, wasn't it?
Yes, 2 years ago or so now already, roughly.
Yeah. I'm just so curious. Sugar as a cryoprotectant, how does that work?
Oh, it's a complicated, very complicated process. So
I won't be able to understand it anyway.
Again, like mainly what we're doing is that the sugar interacts with the water molecule and modifies how the water molecules interact with each other. And
so they're not forming ice crystals.
Yes, and that's a hypothesis. We actually don't know. For a lot of that cryopreservation research, we often don't know exactly how that stuff works. So the DMSO compound has been around since the 1960s. We still don't really know what it's doing. It seems to be doing multiple things, but the exact biology and chemistry seems to be not well understood. So again, like fascinating how little we know. And also water is the most complicated liquid you can imagine. It's not behaving in the same way as other liquids. There are always exemptions, and that's what we basically are made of. Like we're made of water mostly, and when we freeze, that's the main solution that we have to deal with. And so it's really, I think that has hindered a lot of our progress by not having a lot of knowledge how stuff actually works. But machine learning, again, like just taking historic data and feeding it in the system that has no hypothesis, it seems to at least be able to generate no compounds that then we can test. So I see ML also as a hypothesis generating machine. We don't need to know exactly how it works, but by then testing it, seeing it, we can develop new hypotheses, and then also that helps us generate new experiments so that we can test the hypothesis.
But then it's quite frustrating that, as you said, that there are too few people, not enough people working on this problem.
Yes, we basically trying the same tricks or the same strategies that we did in the longevity section. We try now to do in cryopreservation. So we try to talk more about it. We try to kind of like get to young people and expose them to it, explain why it's so important and how it can make such a big impact in the field. But yeah, I think where we fail in the moment is talking to the government and kind of having big grants around it as a big challenge. Like there was the cancer fight against cancer, big thing. A lot of money is being produced. In the UK, we had like fight against Alzheimer. Suddenly a lot of money was around. So like if we could reach top level people that are deciding on budgets, then maybe we have a chance. And I think it's always easy to understand that story. Like bone marrow transplantations are around for a long time. Like if we could make it 50% safer and 50% cheaper, wouldn't that be awesome? Like it benefits the patient, the economy, everyone would be happy. It's an easy win. So, but yeah, the problem is everyone wants money for their kind of research, so it's always competing against other fields.
Well, I hope more people are going to work on it, and I hope that you are successful, because my life might depend on it. I mean, I've signed up for cryo myself, and that's, I think it will be whole body cryopreservation. But, I don't want those toxic cryoprotectants.
Yeah. And you probably also don't know, you don't want them if ever you need like a cancer therapy and you're using one of the now approved T-cell therapies. They're still being cryopreserved in DMSO. Yeah, it's not the best. You're losing cells, you're losing potency of the cells. So it would be nice if we had a better cryoprotectants there. Yeah. But we also have low-hanging fruits in that area. Like, as I mentioned before, like a lot of tissue banks or organ banks. Again, this is linked to generating new biomarkers. So a lot of the materials that we're using to generate biomarkers is usually banked materials. So someone donating part of their body maybe 50 years ago. And so now we have all their life history. We know when they died, but we still have a piece of their tissue around. So now the scientists can go back, analyze that tissue and see, okay, what was different in that person? Why did that person die earlier or later? So we can learn mechanistically more about it. We can develop biomarker based on it. But that tissue needs to be well preserved over 50 years. So again, we're talking a long time. And I think most tissue is currently stored at -80. It's not the best freezing temperature. It's way too high. So I think again, like because the development has not been as quickly, and also because we're not talking to these people yet, they might not even know that there are alternatives around. That they can cryopreserve the material at lower temperatures. But that would be the wish, like that every single piece of tissue that goes into some form of a bank, of an organ bank or a tissue bank, that people are using to develop new biomarkers or to understand mechanisms of aging, that material is well preserved so that it's not aging. At higher temperature, it's still aging. The lower the temperature, basically, the less aging is happening at that frozen state. Yeah. So we should really kind of like, again, it's where like two fields are interacting. The aging world would benefit a lot from having nice tissue that they can analyze. And we would learn a lot from trying to do a better cryopreservation job and making that possible.
So where do you go from here? I mean, now you are, I guess, fully focused on these focused on these areas.
Yeah.
But do you see that there's already now some areas of aging biology that piques your interest, that you want to explore more?
Definitely, I want to kind of recenter around the brain again. So what I'm trying to establish is a better model for brain aging, because I've been very frustrated at working with mice. Old mice, I think, are still better than cells in a dish, but they're the wrong species, and we know like a lot. People have heard a lot like that things that we're developing in a mouse often don't work in humans. So we always say like we have cured cancer or we have cured aging, and a lot of mice we have not cured it in aging in humans. So we know it's a model, and it's a pretty bad model. And people are trying to develop organoids, but then organoids are made of stem cells usually, and they are not old. So they're not really reflecting like an old organism. So what I'm trying to do is coming up with ideas around, okay, how can I have basically a brain in a dish as a model to like test interventions? But that's very, very difficult because it's very complex. Again, you have to have knowledge of a lot of different areas. And that's what I'm currently trying to do, is acquiring all that knowledge that I now need, and acquiring the team to kind of put together a system where we can keep such an organ alive in a dish and can study it. Because what's the benefit from it? I don't need an animal license to it. It's kind of tissue that is coming from like a dead animal, so that makes kind of like life easier in a lot of countries. But it is aged materials. If, for example, you're talking old, large animal models like dogs, would be fantastic. Unfortunately, a lot of dogs die naturally, and so we are thinking of like, could we use this material? So I had a study in the past where I worked with tissue from old dogs, and it's surprising how similar dogs are to humans. And a lot of aging, not a lot, but a couple of aging companies are actually making use of that closeness between dogs and humans. And I think
Loyal, for example.
Yeah, Loyal, for example. So I'm thinking along the same line of like, okay, could we have like a large animal model in a dish, basically, that has naturally aged, where like everything is as it should be. It's kind of aged, and there's nothing artificial around it. but that is not a lie. So I'm not doing any harm. I don't need a license, and I can still test interventions, and I can look at it very, very closely. So I can observe it while it's in the dish.
When you say brain in a dish, I'm thinking of those mini brains that have been in the news. Is it similar?
Think more like organ perfusion. So if I don't know how familiar people might be, but so for organ transplantation, what is happening is that an organ is taken out of a body, it's being put in a machine and basically kept alive in a machine. So it's warm, it's perfused with a liquid, and then it can recover. So that's why it is currently being used. It's like to allow an organ to recover, and then basically also to arrange the clinical side, arranging the transplant and everything. And so it would be the same thing. Like you have basically the brain in a perfusion system.
Okay.
So it is way bigger than what you meant with kind of like little organs in the dish.
Yeah, so I think they call them mini brains in the media at least.
So usually these are made from either stem cells or kind of like induced pluripotent stem cells. So which means you're at very early life because they're coming from a very early stem cell. So it doesn't really matter how much you age them in the dish. They definitely are not 50 years old or not 20 years old. So while people I've seen it like they're trying to put aged cells into these models to kind of mimic aging, but the extracellular matrix is not old. So it's a mixed system. Like it might have some of the feature of an old organ, but not every bit is old.
Okay, I understand. I think that, the first time we met was at the Longevity Biotech Fellowship retreat in Sweden back in January this year.
Yeah.
And you are a mentor to that organization. So what they do is they, among other things, they organize retreats, and they have a fellowship, so you can come there and get educated in all things longevity for a few days. And you are one of their mentors.
Yeah.
And what stood out to me was that they were so focused on replacement and biostasis, which is cryopreservation is one way of thinking of biostasis, right?
Yeah.
And replacement strategy, that the idea is that we should replace tissues and organs and maybe whole bodies. And they didn't talk that much. I mean, they talked about advanced bioengineering, which is kind of, I think, what you would say that you are doing, or maybe the closest thing. But still, they weren't too optimistic about the repair approach. That it's too difficult, and maybe that they also weren't too optimistic about using small molecules as a way forward. So how do you square this coming from SENS and what the Longevity Biotech Fellowship is doing?
Okay, let's start with the Longevity Biotech Fellowship. So I love that activity simply because it's meant to help people find their foot in the field. So it's for people that are coming from a different field than biology or medicine, and they want to get into longevity. So it is hopefully an accelerator of like finding new talent and helping them find their way in the field. Because it's a complicated field. If you don't know it, like how can you learn? Like it's not so much about the education, because education, it's out there once you know where to look and what paper to read. I think it's easy to understand it. But kind of like what we're trying to do is give give them an overview, like what's the field, what's the history of the field, where do I go? And then the mentoring side is just like helping them find their own path, like where they want to contribute, and just kind of guiding them and giving them tips. I think the roadmap was kind of the second level of activity. So now this is a bit combined. So the mentoring and kind of like just kind of bringing talent into the field was the first goal of the organization. Now the roadmap is the second goal, is kind of like, how can we now accelerate progress in that field? And it's a completely different approach to SENS or the Hallmarks of Aging, because what they try to focus on is the more radical approaches. So small molecules, drugs, is a pretty conservative, very well understood field, but might not give a human more than some extra years, maybe 1, 2, 3, 4, 5 extra years. Repair might give you some extra years, maybe some more. And then again, like what Mark is doing and Nathan is looking, okay, what would have like a bigger impact on like lifespan, just instead of just giving a molecule. And so that's, I think, how they came up with the roadmap. And the roadmap is still evolving. It's still developing. So in the moment, they have 3 focus areas. So as you mentioned, the replacement strategy. So basically, that's the idea of like everything that is broken can be replaced. So if the kidney is broken, we just give people a new kidney. And that could be either a tissue-engineered kidney, a lab-grown kidney, or maybe a xenopig, kind of coming from a pig or another animal. All of that might be possible. Or,
and you don't have to understand so much about aging to do that.
Exactly. We don't know. So it's easier if you do it that way, because basically nature grows it for you. You just have to learn how you bring it now back together, how you avoid rejection. So it's still an easier problem, and you might have a bigger impact. So that's one area. The biostasis is basically you put everything on hold by freezing it and wait for science to catch up, and then deal with the problem in the future. So basically that's a problem, put it in the future, and like see that the future will take care of it. And then the third is AI approaches in kind of like all of the areas of aging intervention. That could be small molecules, it could be replacement. Basically, they're just generally looking at like how large data sets in AI could help the field. It's naturally kind of like different because it's mostly cooked up by 2 people. And they are now different people. So I think it's okay that they are different. In terms of which one is better, I think coming back to my initial one, we should put our money on both horses to see which one is the winning one, because we can't afford to lose. So on a personal side, yes, one needs to kind of make a decision which horse I'm riding, and I might lose, but if the society is betting, then please do it evenly, so that we have more chances of success. If the replacement strategy, if you listen to it, it makes sense. Again, nature knows how to grow organs. We don't need to figure that out. So it's easier and cheaper than growing it in the lab. You just have to deal basically with the surgery and the immune rejection. And we're pretty good at that because like science, again, has done that for some years, and it's manageable.
We've been transplanting organs for quite some time now, and I mentioned this, we've had Linus Peterson as a guest. We've talked about the potential PR problem with replacement strategy, that it could be seen as bizarre or something like that we should replace. I mean, if we were doing a whole body replacement, what's your take and response to that?
Absolutely. I think it is definitely a PR disaster if you're not phrasing it in the right way, if you're not packaging it And people are absolutely freaked out. I have that very often. Even my colleagues working in science, if they look at it, they find this very bizarre. So it is natural that people have maybe that reaction to it. So, as I said, that's why it is the more extreme approach. And there is maybe a reason why most people are currently focusing on the less extreme approaches to like get people used to the ideas.
Yeah, it's a leap.
It's very much a leap. I think if you have not thought about it, like, I mean, all of us, we might have thought about this for years and years. So we have becoming very accustomed to these ideas. But for other people that have never seen it, like imagine the people you meet in the supermarket, and then you give them a picture like this, and you say like, hey, how about you want like go shopping for like a new body? And they would be completely freaked out. And so, yes, one has to, again, like, we don't want to scare the public off. We want to explain what's possible, what's not possible, how this is ethical, done or not done. And so I would be more careful because I see how many negative reactions we have. And what we don't want is ban, because that usually is the reaction. Like if something is too extreme, people will block it off and say, okay, this is banned now. And then we would be in a very toxic and hostile situation. And so it's better to explain this bit by bit to people until they understand the reasoning behind it.
But I have to say the Longevity Biotech Fellowship Retreat was awesome. If you haven't been there to one of those, you really should apply. It was the most invigorating 3 days I had for a long time.
Yes, for me is also it's intensive, but because everyone there is so engaged and does want to do something, and that's what creates like a completely different environment. If you go to a normal aging conference or like a science conference in general, people are not that engaged. They usually give their presentation. They may go to like over a coffee talk to like some of the colleagues, but then they go home early to do their normal job. If you go for one of these retreats, you're really there 20 hours a day thinking about it, learning about it, talking about it, because everyone wants to assemble as much knowledge in a short time. They're not there to like, oh yeah, I had some time, I give a presentation and then I go home. Everyone there is really engaged and want to help. And it creates a very nice environment because people also give free tips. They help people find their way. They make job offers. They come together to form companies. They form collaborations. Because, everyone has understood, okay, this is something I want to work on. And now I'm really dedicated to do this. And so here are the people that are also dedicated and willing to do it. And that creates this kind of really moment where there's a lot of energy and enthusiasm and also knowledge, because these are all people that had usually already successes and careers in other fields. They come with a lot of knowledge that is new to the field. And that's what is so brilliant about it.
Yeah, it's wonderful.
What gives you the most reason for hope about the advancement of the discipline, and what are your greatest fears?
Okay, the greatest hopes has just been seeing and remembering how bad it was when I started, and I've now seeing like how this becomes really more mainstream. Even people kind of like in Europe are now more and more leading towards, okay, there seems to be aging interventions, that's okay. Maybe the UK still calls it like a frailty intervention, but that's just a different thing by name. It's still the same thing. So just seeing how the support is growing and how accepted the idea is now in academia. When I started, people called it snake oil and like there's no hope. and now everyone works on some form of intervention. So great successes. Great, fantastic. There is a lot of interest from VCs and people that want to make money. Also great, because that kind of like creates a lot of hub and companies are being created, and that accelerates progress. So all of that, good and positive signs. VCs even come like to Europe, or like European VCs are considering it. Even large pharma is now very slowly and tentatively looking at aging as an intervention field. And they're creating kind of like sometimes collaboration with aging scientists. So again, like fantastic, large pharma is on board. That's a great win. So all of these are wins. The downside is still most of the public is not on board. None of the politicians are really interested. And kind of, there is not enough governmental funding, because VC money is fine, but that usually is spent in a certain way. And what I'm afraid of is that eventually the pipeline, because the discovery pipeline will be empty, because everything that we can work on and intervene in has been translated. But because no one puts money into blue science research, like blue sky research, like we just do research. We don't know what we will come up with or understand or learn. No one wants to put money into that. And that means that eventually we will have no more new knowledge that we can use. So I'm afraid that we have a dry pipeline of preclinical or like even earlier research where, the government is not interested in funding that. And definitely VC will not fund basic research. So who will then pay for that?
But it seems unlikely, no?
Yeah, but I mean, it's in general that things that I see. That's why I mentioned that I always have to promise that I cure a disease at least, or translate something into the clinic next year. So the research money portion that is spent on really hypothesis-free basic research, just anything that you can learn. Maybe how about like water is behaving at low temperature? I think that portion is becoming smaller each year, because the government is afraid of like not having success stories that they can tell their voters. It's like, look, we spent money on cancer, now we cured it. They need these kind of success stories.
But can I ask you, Alexandra, because I mean, there's been a lot of focus on what's called deep tech.
Yeah.
And I mean, there are VCs that are actually pouring money into solving hard problems in energy, for example. And they know that they have to do basic research. It's a long runway. There's no, it's not certain of success and so on. So, I mean, considering what a huge humanitarian problem aging is, doesn't that go back to that we need to be better communicators of how big of a problem this is and why we should solve it?
I think that is definitely one part. The other part is maybe, as you say, tech is better understood. It's something you can touch. It's always behaving the same way. If you break steel, it breaks at the same point of applied forces. So it's kind of like maybe more predictable. Biology is pretty messy. It's very bad to predict what will work or will not work. And what I often hear is that VCs are kind of like, they tech, yes, easy, quick, understandable. Even if like chances are small, they still like, they can judge it. Or maybe they think they can judge it. Like, who knows? Biotech, where there's like tech and bio overlapping, already an explorative area. Usually they say like, okay, I try my hand at biotech. But then going full biology and saying like, now I do like a biology only process. That's kind of maybe further away from like where their natural area of work is. Like a lot of the rich people might be coming from tech area. They have maybe made their money in tech. We don't have a lot of success stories yet of people making their money from therapy in biology. So they then might be more interested in understanding, okay, I need to reinvest money into maybe hard projects. So I think there's also education specifically for VCs, like, okay, getting them used to, unfortunately, messy biotech world, and getting them to understand this is like a slower development process. I can write an app I cannot. Other people can write apps maybe in a month or in 3 months, and you have a product that you can sell. For a biology product to be in clinic and be approved, that's 5 to 10 years currently. So there's education for the public, but also education for the people that are giving money to development.
Do you think it would help a lot to classify aging as a disease?
Maybe. Again, there has been very, very long debate how that now would change everything. It might help. Definitely in the countries where you have governments paying for aging interventions or for interventions in general. But you also have a lot of countries out there where like your health is not covered by any insurance. So they don't need classification. So would it have a big impact? Maybe. Maybe in Europe it would help a lot. But there's activity out there that tries to push for this. And so I think they're making progress. But how much of a big impact that will have is it's hard to say. But I think it's a nice strategy. Definitely clinical trial design. I think that's an area that's kind of very interesting if you talk AI in clinical trial design, where we can save time. Not only talking about like, okay, get rid of FDA, but like, okay, how can we design a clinical trial that is short and very precise and very effective? And so having like loads of iterations and making the process safe and quick. So maybe people could invest in that area, because in the end you can also apply AI to that area, and just I think clever thinking. If there would be a COO that offers this as a service, and I think there are some attempts now of people trying to offer that as a service package. So like the experts of like, how do you best design clinical interventions for the aging space? It would be cool if we would like have like a catalog of like, okay, so what molecule do you have? What area of the body is it targeting? Okay, so this kind of like intervention trial design would be best for you. You just have like a menu, and basically everything is being spit out from like, where do you get your patient from? What clinic is doing it? What biomarker are you measuring? Basically kind of a package structure, so that we are not wasting time on like learning this, because there have been people that have been in this clinical trial area for like many, many years. And I think it would be wasted to not like make use of this knowledge and try to work with them. So if you talk about other areas that we can work in is talk to the people that are doing clinical trial design and ask them like, what would be the best trial design for aging? What's the shortest clinical trial that would show us if an aging intervention works or not? I have always been impressed by one clinical trial where they looked at like how many flu infections a certain population gets. That was like done in a year. So within a year, you had like an answer if that intervention worked or not. That's pretty good. I mean, it's quicker than doing a mouse study on lifespan.
Yeah.
So if people, again, like it's combining the knowledge that we already have and bringing them into our field or making use of their knowledge.
Have you thought about like forming your own company to be this, to create opportunities to get people together from different disciplines to solve a problem?
So in summary, yes. I'm in a lucky position that I work at a university that is not opposed for their PIs and professors to have also companies on the side. So yes, I'm thinking about it. I'm looking for people. It's all about like the team that you're getting together, because that team really needs to be very well aligned to survive the very tough years of like a startup. Which again, like that's maybe a good comment or maybe an outlook for like people coming to the field. There is not an either academia or startups or pharma. You can also have like a life across all of this. And it's specifically the universities in Europe that are very open to this kind of ideas. So my university, very specific, is they're priding themselves of having taught their students on real world problems. So we're always working very closely with companies, and they like us to have actually startups, so that the students learn this very, very early on. Like, okay, there's like the basic lectures, but how you apply that knowledge in real world situation, that's really what people should learn, not like an easy equation. We now with internet can look that up any moment. You don't need to teach that. You can look it up. You even have AI now that uses it for you. So what you now need is creativity, and that you can best teach while you're working on a real problem. So there's I think an interesting niche that is somewhere between academia and kind of startup. So yes, I'm looking. I currently don't have an active startup, but I have an idea in my mind, and if I find the right people and I find the money, which for like the last 2 years has been more difficult, finding that money to start a company. It all needs to come together.
It will change soon. Then you need more than good scientists.
Yes.
For your lab. You also need a lot of different people with different specialities for your new company that you will start, and I'm looking
absolutely.
forward. Alexandra, thank you so much for talking with us today. It's been amazing. We've covered so much.
Thank you for inviting me. It was fun talking to you, and I hope people will become interested in this field and maybe do some more digging around. There's a lot of knowledge out there.
Yeah, and if people want to reach out to you and connect, where can they find you?
Oh, luckily I'm very easy to find. I think my name is unique enough. You just put it in Google and you'll find me. Please feel free to contact me. Reach out.
Perfect. Thank you. Patrick, do you want to add anything?
Well, I was going to ask about if you have any suggestions for how to keep healthy and alive.
Or what I'm personally doing to keep healthy and alive, and maybe
if you have some special scientifically founded unusual advice, perhaps.
Not really. There's this. I think the advice is all out there. There's nothing special I could add to that. Maybe one thing that I always find that people are overlooking is like your stress and sleep cycle, like your circadian rhythm. Is very precious. It keeps your body kind of like aligned, and so a lot of things are happening if you're not sleeping well and regularly, and that's for free. It's something that everyone can do. So maybe that's my advice. Take your time to sleep, even if you feel it's like wasted life.
Do you sleep well, Patrick?
Yes, I do. That's an advice I can follow with pleasure. Thank you,
Perfect.
Alexandra.
Yeah, thank you so much. And hopefully we'll get to talk to you again sometime in the future.
Absolutely. I would be happy to come back.
Okay. Bye-bye.
Bye.